All right, guys, here we go. Example problem number 1, circular motion. Thing here is you have to remember that centripetal forces are going to be some other kind of force. Here, a pumpkin astronaut, of course, it's just after Halloween, so a pumpkin astronaut is orbiting a newly discovered Earth-like planet. The orbiting is going in a circle, but the force that becomes the centripetal force, what keeps anything in orbit around a planet or a planet around the sun, it's the force of gravity. Gravity becomes the force of gravity is the centripetal force. This is the general, really important concept behind all of this stuff. That the centripetal force is some other force. In this case, it's going to be gravity. So here we go. As always, you start problems in physics by drawing a picture. And in this picture, we've got a planet and a pumpkin orbiting the planet. This pumpkin has a mass of 500 kilograms. Let's say he's orbiting this way. That doesn't look anything like a circle, but that's okay. It's orbiting this way. And it goes a complete circle, complete orbit in 12 hours. So the period of revolution is 12 hours. And the distance above the surface, well, my diagram is totally not to scale, but here we go. This is 5 times 10 to the third meters. And the radius of the planet, again, this is totally not to scale, is 3.5 times 10 to the 4 is considerably larger than the radius. I didn't draw this thing well at all. Is 3.5 times 10 to the fourth meters. All right, and there we go. So the thing is to recognize that from the center of the planet to here is this radius is going to be 5 times 10 to the third plus 5 times 10 to the third. That's how many meters it is above the surface, plus the radius of the planet, which is 3.5 times 10 to the fourth meters. So the distance the pumpkin astronaut is from the center of the planet, 5 second 3e plus 3.5 second e4 is going to be 40,000 meters. Okay, R is really 40,000 meters, or you could say it's 4 times 10 to the fourth meters. That is the distance the thing orbits. Okay. All right, now we're ready to actually start the problem. To start the problem, we want to know the speed of the pumpkin. Well, speed is not a complicated concept. Velocity equals distance divided by time. What distance does an orbit encounter? Circumference, right? The distance is the circumference divided by the time. The circumference is 2 pi r. The time is the period of revolution, which in this case is 12 hours. So 2 pi times r, 40,000 meters, divided by 12 hours. But we don't give our answers in meters per hour. We want to have our answers in meters per second. So we have to convert 12 hours into seconds. And for every 1 hour, there are 60 minutes. And then that's supposed to say an hour. Then for every 1 minute, there are 60 seconds. So 12 hours times 60 minutes per hour, and then multiplied by 60 seconds per minute is 43,200 seconds. So our speed is really 2 pi 40,000 meters divided by 43,200 seconds. So here we go. Let's do this arithmetic. 2 pi times 40,000 gives us that number, whatever, divided by 43,200 seconds. So we get the speed of the planet to be 5.82 meters per second. Speed of the pumpkin astronaut, 5.82 meters per second. Distance divided by time. Next part of the problem, mass of the planet. This is a little trickier. Not much, but this is where you really have to recognize what we were saying before, that the force of gravity is the centripetal force. The force of gravity is the universal gravitational constant times the mass of the planet times the mass of the astronaut divided by the separation between them squared. The centripetal force is the mass of the astronaut multiplied by, remember this, centripetal force equals m times centripetal acceleration, and the centripetal acceleration is v squared over r. So centripetal force is really mass multiplied by v squared over r. So the mass of the astronaut multiplied by the velocity of the astronaut squared divided by r. How far away it is from the center of the planet. So now a couple of things here are going to cancel out. Mass of the astronaut, on both sides of the equation, that vanishes. This r and one of those r's, right? That was really r times r. So that cancels out one of those r's. So that's very nice and useful. So our equation is going to become something like the universal gravitational constant times the mass of the planet divided by r equals the velocity of the astronaut squared. We have the velocity of the astronaut. We know this. We just figured that out. G is a universal constant. R we figured out was 40,000. That will allow us to solve for mass of the planet. Or to get mass of the planet, right? So when we get the mass of the planet, that's what we want to solve for. When we bring G and R over here, basically we're going to invert and multiply. So we're going to get the mass of the planet to be equal to the velocity squared multiplied by r divided by g. So 5.82 meters per second squared times the separation, which was 40,000, right? 40,000 meters divided by g, 6.6. No, what is that? That's not the, is that the same thing, the separation? Yeah, by this is the number. For some reason, I was thinking I had to use 3.5 times 10 to the fourth, but no, you use that because it was the centripetal force on the astronaut. So that number there, and 6.67 times 10 to the negative 11th newtons, meters squared per kilogram squared. Here, a bunch of things are going to cancel out. We're going to end up with a unit in kilograms. Meters squared per second squared. There's meter squared. Second squared is in newtons over here. We got an extra meter. Kilograms is in the, it's going to cancel out with the kilograms squared here. It's all going to work out. So doing the arithmetic, doing that math, 5.82 squared times 40,000 equals that, divided by 6.67 times 10 to the negative 11th. Not a very massive planet. Mass of the planet equals 2.03 times 10 to the 16th kilograms. That's the mass of the planet. 2.03 times 10 to the 16th kilogram. All right. Then the acceleration due to gravity on that planet. The acceleration due to gravity on the planet. The gravitational force is G, M planet, M object, divided by the radius of the planet squared. Here's all of this is the acceleration due to gravity on that planet. Just like we say F of G equals mg, the mass of the object times g. G is all this other stuff. All of this other stuff is the acceleration due to gravity. On Earth, all of this other stuff works out to be 9.81. But on this planet, what is it going to work out to be? G is still G, 6.67. The mass of the planet we just figured out to be 2.03 times 10 to the 16th kilograms. And the radius of just the planet, this is where I was paused last time. It's just the planet now. You don't need this piece with where the altitude of the pumpkin. So this, the mass of the planet, the radius of the planet rather, is 3.5 times 10 to the 4th. 3.5 times 10 to the 4th meters squared. You do this arithmetic, we get the acceleration due to gravity on the planet, 6.67 second e negative 11 times 2.03, oops, hit the wrong button, 2.03 times 10 to the negative 16th equals that, divided by 3.5 second e4 squared. Gives you something ridiculously small. Holy cow. So this is tiny. 0.0011. Okay, this is like the most ridiculous planet there ever was. And the units for this would be in meters per second squared. .0011 meter per second squared. And the last question, what would the astronaut weigh on the surface of this planet? So now we can plug that back into this equation to find the weight, right? F sub g equals mg. M, I think it was a 500 kilogram pumpkin, times 0.0011 meter per second squared, about 0.55 newtons. That would be his weight. .55 newtons. All right, guys. The big thing is to equate the gravitational force as the centripetal force.